Methane is the main component of natural gas in chapter 3. Okay, now we are in chapter 3. It is also a greenhouse gas. Okay, cattle raising is one of the sources of atmospheric methane. So write down two other sources that can release methane to the atmosphere. You can also consult the Wikipedia. Hope you actually went to read it. So if you read the article, you would find that methane are actually produced by a lot of microorganisms. For example, you can find them in ponds. There's some bacteria that will generate methane gas. So one of them is from microorganisms such as bacteria that will produce methane gas, methanogenic bacteria. Okay, you can find them in some kind of ponds. Okay, there's also a lot of methane stored under the ocean, and sometimes some kind of movement of the earth plates can disturb the bottom of the ocean and can release a bit of that methane. So it could be released from methane stored underground. So methane stored underground in oceans. Okay, I don't know if the English is good there, but never mind. Get the idea. Okay. Okay, so let's do a real question. Methane has a GWP, global warming potential, of 72. It's a much better greenhouse gas than carbon dioxide, which has a GWP of 1. Give two reasons why the GWP of methane is higher than carbon dioxide. Okay, so the two reasons of that. The first one is to do with absorption of infrared radiation. Okay, so methane is a much better absorber of infrared radiation. More infrared radiation than CO2 because it has a tetrahedral shape. And you can also say that CO2 is linear. So there are more of these vibrational modes that can lead to a change of dipole moments or change of charge distribution. So because it is tetrahedral compared to linear, so the way there are more manners in which it can vibrate to lead to absorption of IR. Remember, to absorb IR, you need to have a change of dipole moments or change of dipoles. Okay. The proper term is dipole moment, which calculates the bond length as well as the charge distribution. But because I didn't define this term, so I'm reluctant to use it. But I used it in the notes, so I put it here. So the second part is the second reason for it, because GWP doesn't just take into account of amount of radiation absorbed. Okay, that just tells us whether it's a good greenhouse gas or not. Okay, but global warming is also dependent on the lifetime of the gas, whether it stays around for a long time or whether it's removed quickly once it's formed. So compared with carbon dioxide can be removed quite quickly by what? By rainwater, because it dissolves in rainwater. Okay, and then you can wash it away. We already saw the reaction of carbon dioxide and water in the question in chapter 1. So this is because methane has a longer lifetime in the atmosphere. It's not soluble in water, whereas CO2 can dissolve in a little bit, dissolve in rainwater. So the 2 point is infrared radiation absorption and also the lifetime. So GWP is a factor that takes into account of both. Methane present in natural gas is commonly used as a fuel. And in Hong Kong, our town gas actually contains around 28% of methane. Write a chemical equation for the complete combustion of methane with state symbols. Okay, so specifically you have to put state symbols here. Methane, burning the methane. Today we already talked about combustion, so we have to add oxygen to the formula, and then we burn and produce carbon dioxide and water as the products of complete combustion. So then we have to balance the equation. Now what is not balanced is the hydrogen. There's 1 here, there's 2 there, and also oxygen as well. There's 3 there and 2 there. So we have to firstly, let's take care of the hydrogen by putting a 2 in front of the water. And then we can come back to the oxygen here. There's now 4 oxygens on the right side, so that need to be 2 O2 on the left side. Then we need to put in the state symbols. Methane and oxygens are gases, and it forms carbon dioxide as a gas, and water in this case is also formed as a gas. As you know, when you burn something, the water comes out as a vapor, okay, rather than liquid water. So town gas also contains hydrogen. Explain why hydrogen is a fuel that does not cause global warming. Okay, so hydrogen, when it burns, very easy to answer this, because when hydrogen burns, it forms only water. You can balance the equation. And water is not considered as a global warming causing gas, because although it absorbs a lot of infrared radiation, is responsible for the major part of temperatures of room temperature, of retaining temperature. But water has a constant concentration in the air. We cannot change, we cannot increase artificially the amount of water in the air. Okay, extra water will just go into the clouds and then finally drops down as rain. Okay, it's controlled by humidity. So there's a limit to how much water vapor can there be. Okay, so it's not going to. So water is not considered to cause global warming. Only CO2 is considered as a global as a source of global warming. Okay, second question is about acid rain. You need to explain how the following pollutants are formed when coal is burned. So burning of coal causes acid rain. Sulfur dioxide is formed, and this is formed because the coals contain some sulfur impurities. So there are some impurities of sulfur in the coals. So when these sulfur impurities burn, SO2 is formed. For the nitrogen dioxide, it is not quite that there is nitrogen impurity in the coal, but instead it is a reaction that happens between nitrogen and oxygen in the air when you have a high temperature. When you have a temperature greater than 1000 degrees, which is provided by the heat, the burning of coal. And of course, this is about nitrogen dioxide, so you have to also say that NO actually reacts with oxygen in the air to form NO2. So you can also express this in terms of two equations. Okay, so you can write equations as well, all the words. Next question, you have to write some equations to explain how acids are formed when these two gases dissolve in water. So these are equations that you can find in the notes, but it's also easy to work out the answers. So there's reaction with water. So sulfur dioxide reacts with water, and you just add up the atoms to get H2SO3. Okay. And this is called sulfurous acid. And for nitrogen dioxide, NO2 plus H2O. This one is a little bit more difficult because you actually form two different acids. You form HNO2 and HNO3. And of course, in this case, you need two of the NO2. This one is called nitrous acid. This is nitric acid. Okay, so rainwater collected from a village region of the rural parts of China has a pH of 6.0, while rainwater collected in an industrial region has a pH of 4.7. So although both pH values correspond to weakly acidic, only this 4.7 value is considered as acid rain. So explain why rainwater with pH 6.0 is not considered as acid rain. Well, because normal rainwater also is slightly acidic because of the carbon dioxide, right? So carbon dioxide will dissolve in normal rainwater. To form carbonic acid, which is a weak acid. And the pH is around 6. So this is clean, okay? This is not pollution. So this is natural rainwater. Question D is substances containing phosphorus are burnt in a flame. For example, in a waste incinerator, phosphorus pentoxide, P4O10, would be produced as a fine dust. So if these fine dust particles dissolve in rainwater, phosphoric acid will be produced. Write a balanced chemical equation for the reaction. So you need to again formulate an equation from some given information. So basically, P4O10 is now reacting with the rainwater H2O to form phosphoric acid H3PO4. And the most difficult part of this question is just getting this to balance. Okay, it's a bit of a tricky one. And surely after your a bit of struggle, maybe, then you should find that the balancing numbers is 6 and 4. If you want to put the state symbols, you're also welcome to. The solid is, this is fine dust, solid, rainwater, liquid for H2O, and this is dissolved in water, so it's AQ. Third question about Freon 11. So chlorine is an important raw material for production of CFCs. So you have to write a balanced equation for the chemical equation producing freon 11. So it's usually made from methane reacting with fluorine and chlorine. So to balance this equation, there is actually more than one way to do it. Okay, I'll just give you one of the possible answers. So because there are 3 chlorines there, so you have 3 of these Cl2, and that will lead to HF plus 3 HCl. And there is more than one way to do this. So check yourselves that the number of atoms balance on both sides, and you are fine. CFCs such as freon 11 are now banned from being used. And the main reason for this is because they have an effect on the ozone layer. So they will explain what happens. So CFCs depletes the ozone layer. Or you can say that it destroys ozone. Or you can say it lowers the concentration of ozone. Anything similar to this? Why is it worrying to our health? Well, because with a thinning ozone layer, more harmful UV radiations will come down to the surface of Earth. And this can increase the risk for skin cancer or eye diseases, such as cataract. So after CFCs were phased out, some replacement were introduced. Firstly, the ones called HCFCs, hydrochlorofluorocarbons, and then finally HFCs, hydrofluorocarbons. Explain why HCFCs have a lesser impact on the environment when compared to CFC. So the reason for adding the hydrogens in the molecule is to reduce their lifetime, make it less stable. Okay, so if you say the HCFCs have a shorter lifetime in the atmosphere. Okay. So less of them will arrive to the ozone layer. Okay, so some more of them will be decomposed or washed away or broken down in the atmosphere before it goes up all the way to the ozone layer. So why HCFCs are not ideal replacements, which are now also banned, and HFCs is acceptable? Well, because HCFC still has the chlorine, which is still has chlorine atom. So it can still form the chlorine radical, which can destroy ozone layer. But there's no chlorine atom in HFC, so it's acceptable. It doesn't harm the ozone layer. So it doesn't harm the ozone layer. Okay. A lot of writing. Don't worry, get a copy later. Okay, so you don't write it down now. You can download it tonight. Then we have to do some chemical questions. Now, when a molecule of freon-11 arrives to the stratosphere, it reacts with a molecule of ozone, okay, turning it into an oxygen by a chemical reaction. So it involves breaking chemical bond by light and then forming some radicals. What is the type of radiation that causes the chemical bond to break? Well, it is the UV radiation. Okay, so you have to say it's UV radiation, or if you're more specific, you can say it's UVC, which is the higher energy UV radiation. Write an equation for the process of breaking this bond, okay, and use a dot for the radical. So we have freon 11, CCl3F, or if you want, you can draw it. And this breaks down into one of these CCl bond breaks. Okay, so you're left with CFCl2 as a radical plus the Cl radical. Okay, so one of these bonds breaks apart. So what is a radical? A radical is a species with an unpaired electron. It is not a species with a single electron or some kind of people say lone electrons. So those are not the term to use. Unpaired is the word, okay, because it is not paired up with anything. Single electron means you only have one electron. Okay, like hydrogen. Lone electron, I don't know what's that, a lonely one. Okay, let's try to finish the last question of chapter 3. That's 2 questions actually. Okay, taking you to London on a jet. So this question is about a flight to London on one of the largest aircrafts. So when you travel on an airplane, the airplane engine burns jet fuels, and it's usually jet A1 fuel if you are aware of the aviation stuff. So let's assume that the fuel is kerosene. Okay, the fuel is actually kerosene. We'll learn about this in chapter 6. And the number of carbons is from 8 to 16. So that would be an average number of carbon of 12. Let's assume that all this hydrocarbon in the kerosene is a C12H26 just for convenience. So write the balanced equation for complete combustion of dodecane, which is C12H26. So again, combustion react with oxygen to form carbon dioxide and water. So the difficult part here is to balance the equation. So to balance it, always start from carbon to carbon dioxide, 12 of these, because 12 carbons, and then hydrogen to water, 13 water, and then come back to the oxygen at the end. So if you do this, you will find out that you need 18.5 O2 because there are 37, I suppose, oxygens on this side. How many moles of oxygen is needed to burn 1 mole of dodecane? Well, from this equation, you can see 1 mole of dodecane, you need 18.5 moles of oxygen. So if 1 liter of dodecane contains 4.4 moles, so this is given to you, so because a liter, you have to take into account of the density. So now you know that 1 liter contains 4.4 moles of dodecane. How many moles of oxygen will be needed to burn 1 liter of C12H26? So because it's dodecane to oxygen is 1 to 18.5. So if we have a 4.4 here, this is going to be 18.5 times 4.4. Okay, so moles of O2 equals 4.4 times 18.5, which is 81.4 moles of O2. Okay, so you need 81.4 moles of O2 to burn 1 liter of the fuel. the jet fuel. So the interesting question comes, the typical cruising altitude for a long-haul flight would be 35,000 feet. At this feet, the atmospheric pressure would be 0.24 atmosphere. So meaning that it's 24% of the normal atmosphere at the given sea level, compared to sea level. So given that 1 liter of air at 1 atmosphere contains 9.38 millimoles, okay, this is milli, okay, moles of oxygen, which is, 21% of oxygen. And then we can work out how much oxygen is in 1 liter of air, which is 9.38 millimoles. Work out the volume of air before compression by the engine, okay, that was needed to burn with 1 liter of dodecane at cruising altitudes. So, complex question, right? Trying to get you to figure out the answer. Very complicated one. So, you need to go back a few steps, okay? So, firstly, the first one is, you know that to burn 1 liter of dodecane takes 81.4 moles of O2. So if it is at 1 atmosphere pressure, it contains 9.38 millimoles of oxygen in 1 liter. So that's 9.38 times 10 to the minus 3 moles of O2. If you are at cruising altitude, 35,000 feet, the atmospheric pressure is 24% of the 1 atmosphere. So it would contain only 24% of this amount of oxygen. So 1 liter of air contains 0.24 times this moles of oxygen. Which is 2.25 times 10 to the minus 3 moles of O2. So now you can work out a ratio. If you wanted to have 81.4 moles, how many liters do you need? Therefore, you need 81.4 divided by 2.25 times 10 to the minus 3, which is 36158 liters of air at 35,000 feet. So you need a large volume of air to burn 1 liter of fuel at the cruising altitudes. Now, of course, if the engine malfunctioned, air supply to the engines will be reduced, and sooty orange flames can be seen from the engines. So in the passenger in the cabin may also smell the fuel, okay, because the fuel is not burning properly. So this sometimes is known as engine surge in terms of aviation issues. So it might be quite scary when you look out of the window and there's some flames and black smoke coming out of the engine, and then you smell some fuel, you think you are going to die. Okay. So so hopefully this doesn't happen. So you have to name this type of why we see these sooty orange flames, what is the type of combustion, and give 3 pollutants that are emitted when this type of combustion occurs. Of course, this is when air supply is limited, okay, so it's not enough air there. So this is incomplete combustion. And there are 3 different particles, that substances that can be produced, such as soot, carbon particles, carbon monoxide, and also unburnt fuel vapors. So when you have incomplete combustion, you have these. This is a type of VOC, okay, volatile organic compounds. Okay, so this is an interesting question. So the largest aircraft is the A380. Okay, it can carry 525 passengers per flight. So for a typical flight from London to Hong Kong, Hong Kong to London, whatever, okay, it consumes around 200,000 liters of jet fuel. Okay, this is information I gathered from the internet. So assuming the fuel is dodecane, let's use the information we calculated to find the amount of carbon dioxide in kilograms that will be released in this flight. So basically, we have the equation already from previous. We know that C12H26 is reacted with 8.5 moles of O2 to form 12 CO2 plus 13 H2O. So now we are interested to know that when we have 200,000 liters of jet fuel, how many CO2 is produced? Okay, so first we need to know the moles of dodecane. In this case, we don't work it out by mass or whatever, because we already know the relationship that 1 liter of dodecane contains 4.4 moles. So we need to divide this by 4.4 times this by 4.4 moles. Okay, and that will give us 880,000 moles. And then we use the ratio of the dodecane to CO2, and we know this is 1 to 12. So the moles of CO2 would be 880,000 times 12. So we get 1056,000 moles. It's a large amount of moles of carbon dioxide released when we burn 200,000 liters of fuel. We get more than 10 million moles of carbon dioxide. So the mass of this carbon dioxide would be moles times the MR. So moles is very big, this number. MR of carbon dioxide is given to you already in the question to save you time. It's 44. And that is 464,640. If you want it in terms of kilograms, then you have to divide this by 1,000, right? Because we get grams. So if you divide it by 1,000, you get this amount of kilograms. So this is the amount of carbon dioxide released in one flight from Hong Kong to London. So what is the carbon footprint of each passenger? There are 525 passengers. So it means that how many kilograms of CO2 is released per passenger. So we have to divide this by the number of passengers. Divided by 525 passengers. That gives us 885 kilograms of carbon dioxide per passenger. Okay, so you are feeling guilty. You're releasing a lot of carbon dioxide, contributing to global warming and the fate of the Earth by flying to London. So when you buy a ticket, the air flight company very kindly help you to feel less guilty by inviting you to pay for an option to offset your carbon footprint so you can fly carbon neutral. How nice of them. Of course, you pay more money, and they say that the money you pay will be used to plant 25 trees. And of course, somehow planting the trees will help offset your carbon dioxide emission. Why? Why does this happen? What is the chemical process that trees use to remove CO2 from the air? Well, of course, we know this is photosynthesis. So trees undergo photosynthesis, and we can convert carbon dioxide into some kind of organic molecules, such as glucose, and form oxygen, so to balance the equation. And sunlight is needed for this photosynthesis. Suggest 2 other alternative ways to reduce carbon dioxide emission instead of planting trees. What else could you do? Well, a few things. For example, use nuclear power or other renewable energy sources. So here you could suggest solar power, wind power, okay, things like that, instead of burning fossil fuels. So use nuclear fuel or other renewable sources instead of fossil fuel. This is one thing. Another thing, very easy for yourself, is to perhaps recycling your waste. That would be a good way as well. Let me put the calculation up because this is a bit more complicated. Just one more question and then we'll finish. You're all tired, right? Sorry. Me too. But otherwise, we are left with one question, and it's kind of not nice. Okay, so let's finish this sunscreen chemistry question. So the first one is this moisturizer with SPF 30 and has a lot of ingredients, and this is the one which is active ingredient for sunscreen. There are a few of them: avobenzone, homosalate, etc. And one of them is octocrylene. So this is structure of octocrylene, where we want to identify the parts which allows it to absorb UV light. So it is those conjugated systems. So it is this part, okay. So this absorbs UV, and because it has a conjugated system, this is alternating double and single bonds. Okay, so you learn how to read structural skeletal formulas. So you have to work out the formula of octocrylene from the structure. And I don't know if you tried. So the answer I give you now is C24H27O2N. Okay, so it doesn't really matter the order of the elements. Okay, so but numbers should be correct. Hopefully you get it. And the product states the following: it also contains advanced sun protection, blah blah blah, to protect your skin from UVA and UVB. So state which type is more harmful in terms, and explain in terms of wavelength and energy. So of course UVB is the more harmful one because it is shorter in wavelength and higher in energy. Than UVA. Okay. The ozone layer is kind of like the Earth's sunscreen. It protects us from UVC and UVB. So the active ingredients in this sunscreen is oxygen and ozone. So identify the molecule that absorbs UVC and the one that absorbs UVB. Explain the reason in terms of bond strength. So here we know that O2 breaks down, okay, to form oxygen oxygen atoms, and we are breaking the OO double bond. Ozone also breaks down to form oxygen gas and oxygen, and we break the O and 1.5 bond. Okay, so this is a weaker bond, so it will absorb lower energy UV. So therefore this must be the UVB, this must be the UVC, the stronger bond here. 1.5 bond. Okay, just 3 calculations and we're done. So this is to do with some bond strength calculations and light energy. Okay, so the first one is about the energy needed to break the OO bond in O2 and O3. So it's told to you that the bond strength of O2 is 498 kilojoules per mole, which means it takes this amount of energy to break 1 mole of the OO bond in O2 and 364 for OO bond in O3. So if you want to know how to energy needed to break 1 single oxygen bonds. How do you do? Well, because this is per mole, so first of all we have to divide it by the mole, and this is in terms of kilojoules, which is 1 times 10 to the 3 joules. Okay, so we need to convert this as well. So for O2, this is 498 times 10 to the 3 joules of energy divided by number of moles. Okay, Avogadro's number, 6.02 times 10 to the 23. So we'll get 8.27 times 10 to the minus 19. So remember, a mole is and then do the same for the O3. Okay, so the frequency of the photons can be calculated according to this, because to break one single bond, it will absorb 1 photon, the energy of 1 photon. Okay, so we can actually work out the frequency of the photon if we correlate this to the energy of the photon. So we have the equation E equals h nu. Remember this equation. This E is the energy of the photon. This h is Planck's constant number, and nu is the frequency in hertz. This is given in data book. So if we want to work out the frequency, then the frequency would become E divided by h. Okay, so for O2, this will be 8.27 times 10 to the minus 19 divided by Planck's constant, which is 6.63 times 10 to the minus 34. Again, this is in the data book. So this gives us 1.25 times 10 to the 15 hertz. For O3, then this is 6.04 times 10 to the minus 19. This is the energy we calculated, divided by Planck's constant, which is 9.11 times 10 to the 14 hertz. These are the frequencies of the photon. For the exact energy. So the wavelength of the photons, you have to calculate it. So we have to use another equation. C equals nu times lambda. C is speed of light. Nu we know is frequency. And lambda is wavelength. So if we rearrange to work out wavelength, the wavelength is C over nu. And in this case, we can work out that the wavelength will be 3 times 10 to the 8 divided by 1.25 times 10 to the 15 for O2, which is 2.4 times 10 to the minus 7 meters. This is speed of light. Yeah. And then for O3, we have 3 times 10 to the 8 speed of light divided by the frequency we worked out from above. So this gives us 3.29 times 10 to the minus 7 meters. In the notes, we used nanometers as our unit. 1 nanometer is 1 times 10 to the minus 9 meters. So we have to, if you want to work this out in nanometers, you have to times this by 100. Take the decimal place twice. Okay, so this is also 240 nanometers. This is also 329 nanometers. So you can classify these into the UV. Okay, so if you actually look at the table, this is UVC, and this one falls in between UVA and UVB. Now, of course, these are just the minimum energy needed. Okay. These are the minimum energy. Okay, so you can also go a little bit shorter in the wavelength to break the bonds higher in energy. Okay, so it usually tend to be UVB, okay, for the ozone and UVC for oxygen.